car moving at 30 meters per second, 1,500 kilograms, and it encounters 1 kilogram of water, which I've represented by a blob of water. It's moving downward at some velocity. That's v sub water. I can't hardly read it, so I don't know that you can. Of course, that velocity is perpendicular to the motion of the car, and we're just going to apply the impulse momentum theorem in the horizontal direction, so the vertical velocity has no effect. In the real world, hitting a slanted windshield and so forth, but we're just going to model this in terms of the amount of water that ends up on the car. So in 1.6 seconds, we assume that 1 kilogram of water ends up on the car, and we want to find the impulse of that force on the car. Now, the water is actually presumably distributed in drops, a lot of drops, because that'd be pretty heavy rainfall in order to do what the water does here, but a conceivable amount of rainfall. And there's more to it in the real world. I didn't mention in class, but a lot of the water that the car encounters doesn't end up on the car. It ends up scattered around, and each collision with the raindrop is only a partially inelastic collision, and that all gets fairly complicated. So right now we're just considering the effect of the 1 kilogram of water that ends up on or in the car. Okay, so the impulse of the car on the water is F12. Now we're going to regard the car as object 1, the water as object 2. So it's the force exerted by the car on the water, force exerted by the first mass on the second, times delta t, is the change in the momentum equal to the change in the momentum of the second object, because that's the object on which the force is being exerted. So that calculation is very simple. And we find that the F delta t is 30 kilogram meters per second. And we calculate the mass times velocity to get that. Okay, I believe that's right. So the impulse of the water on the car, because that was the question, we found the impulse now of the car on the water. Impulse of the water on the car will be equal and opposite to that, won't it? So we see F21 delta t is negative F12 delta t, because these two forces constitute an action-reaction pair. And of course, these are average forces, because the actual forces are discrete. Every raindrop collision exerts a force, and every raindrop sticking to the car exerts a force that contributes to what we're doing here. So in any case, the impulse of the force on the car is negative 30 kilogram meters per second. And from that, we know that the change in momentum of the car is negative 30 kilogram meters per second. So we have mass times change of velocity of the car equal to negative 30 kilogram meters per second. We find the change in velocity by dividing the negative 30 kilogram meter per second impulse by the mass, which gives us the change in velocity, negative 0.02 meters per second. And we're asked, how long does it take to change the speed of the car, let's say, or to decrease the velocity of the car by 4.4 meters per second, which is roughly a mile per hour. Well, this decreases it by 0.02 meters per second. We want to decrease it by 0.4 meters per second. So the first obvious approximation that we're going to make is that this has to happen 20 times. And the assumption is this continues. Now, a little ambiguity in what this means. Does this mean the change in momentum, or does this mean that we keep accumulating a kilogram of water every 1.6 seconds? Well, we're not going to get into the finer points, except in the starred problem, the asterisk part of the problem. But we're just going to go with this estimate. Now, in fact, as the car slows, it's not slowing much, it's slowing by 3%, but as it slows, it's presumably going to encounter less water, and even if it encounters the same amount of water every 1.6 seconds, it's going to be encountering it at a little less velocity every time. So in order to get a more accurate estimate, we'd actually have to do an integral, but it's not going to differ. The result is not going to differ from just multiplying well, by assuming that if we do this 20 times, we get the change in velocity that we want, okay? So, each time this occurs, it requires 1.6 seconds. So, we lose 1 mile per hour in 20 of those, which would be 32 seconds. Now, if you want to go ahead and set up the integral with some kind of a functional approximation, assume a constant rate of water accumulation, you are welcome to do so. But your result won't differ from 32 seconds by more than maybe a second or so. Okay, so that's the idea here. And the big idea, again, is we use the impulse momentum theorem. Some people wanted to calculate the acceleration, and that's maybe feasible, but you'd have to make certain assumptions, and it's not necessary. We bypass the need to calculate any accelerations. Now, if you wanted to calculate the average force, well, it turns out that that can be calculated rather easily. Delta t is 1.6 seconds, so we divide this by 1.6 seconds, and we get an average force of about almost 2 newtons.